Now in this video, we are going to discuss about the Ohm's law and Kirchhoff's law and some examples for applying the Ohm's law and Kirchhoff's law. Now Ohm's law states that under constant temperature and pressure, current flowing through the conductor is directly proportional to the voltage applied across it. So if you take a resistor like this or a conductor like this, and in this conductor we have two terminals, one is here, another one is here, and if you pass the current from one terminal and it passes the current through this conductor and leaves this terminal, and when this current flows from this terminal to this terminal, the magnitude of current is proportional to the uh, voltage applied across this is the Ohm's law under constant temperature and pressure, right? Therefore if you mathematically represent it, it gives you expression like this: I is proportional to V and I is equal to V by R is a proportionality, where 1 by R is called as a proportionality constant, right? So or this, you can, other words, you can write it as V is equal to IR. Generally we write it like this, right? Both the equations are one and the same, and where this R is represented as resistance of this conductor. Therefore the power dissipated by this resistor is given by power in an electrical circuit is given by voltage multiplied by the current. Therefore either you apply the voltage in place of voltage, you apply the voltage here, or you may apply the I also. Yeah. So what is I here? What is I in case of a resistor? I is equal to V by R. You substitute V by R here, then what we'll get is V into V by R will give you V square by R, this expression. Or in place of I, you substitute V, in place of V, you substitute IR, then what will get IR into I is equal to, that is power is given as I square R. Therefore, the power dissipated in a given wire or a resistor can be expressed as V square by R or I square by R. If V is positive, then it will be plus V square by R and V square R, or plus I is positive, then it will be I square R. So whether the voltage or current are positive, if you look at these two expressions, but ultimately the voltage, whether it is a negative or positive voltage, ultimately the power dissipated will be the same in a resistor, right? And this is about the Ohm's law. Then we have a Kirchhoff's laws. Kirchhoff's has two laws, stated two laws. One is Kirchhoff's current law, another is Kirchhoff's voltage law, right? KCL, generally we call it as KCL, KVL. Let us first we discuss about the KVL, Kirchhoff's voltage law. So what does Kirchhoff's voltage law state here is, this law is related to EMFs and voltage drops in the circuit. It is stated in the circuit as the algebraic sum of all the voltages in a closed path is zero. So you take any closed path in the and the algebraic sum of the voltages in a closed path is equal to zero. So in this example, if you take this circuit where you have a source here with plus and minus, all right, and these are all some passive elements, maybe resistor, inductor, capacitor, which we have discussed earlier, right? Therefore, so whenever current flows in a circuit or in a passive elements, so we all know that the voltage will drop. So when does the voltage will drop? The voltage will be dropped when the potential is dropping. That means when the current is flowing in this direction, right? In this element may be resistor or inductor or capacitor, whatever it is. So the entering terminal would become positive and the leaving terminal would become negative. Similarly, in this one also, in this box where you have a passive element, here also the current is entering, the enter terminal will have a positive voltage and leaving terminal, current leaving terminal will be negative. And in this terminal also you have, in this box also you have plus and minus, since all these three are passive elements we have assumed it as, right? So under this condition, right, let us we apply the Kirchhoff's voltage law. So the algebraic sum of the voltages in a given closed path is zero. This is the statement of the Kirchhoff's voltage law. So let us we'll take the current is flowing in this direction, right? Then let us we apply the, so we have taken the direction of the circuit is in this direction. So as the current in this voltage source is flowing from negative terminal to positive terminal, in general convention, if the current is flowing from negative to positive terminal, we treat that as a positive voltage rise, that we call as a voltage rise. If the current flows negative to positive, current I flows, it is voltage rise. If the current flows from positive to negative, negative to positive, voltage rise. If current flows from positive to negative, it is voltage drop. Now the same convention here also will apply here. If you look at this, the current here, the current is flowing from negative to positive. Therefore, I took this as plus V. Then here you look at, come to here the V1, the current is flowing from negative to positive. So you take it as a minus negative sign, voltage drop as negative sign V1. And similarly here also plus 2 minus, the current is flowing minus V2. And here also the current is flowing on plus 2 minus V3. So the algebraic sum of all these three voltages is equal to 0. Or if you rewrite this equation, V is equal to V1 plus V2 plus V3. So what we can write here, it is the algebraic sum of the voltage rise. It is voltage rise is equal to algebraic sum of voltage drops. So the same expression here we have written here. So your KCL can also be spell it out in this way. The sum of the voltage drops is equal to sum of the voltage rises. So this is what we have right here. We have mentioned here. Right. Next, this is the Kirchhoff's voltage law. Then let us apply the Kirchhoff's voltage law to this circuit. For this example, you take this example where you have two voltage sources. You have two voltage sources. One is this, and the one is this. Right, and a current is flowing in this direction. We have assumed it that. Now, when you take the current is flowing in this direction, like this clockwise direction, CW clockwise direction. Therefore, this V1 is rising, and whereas V2, V3 are dropping, and V4 is rising. Therefore, if we apply the Kirchhoff's voltage law, and V5 is dropping also. So we can say here, look at this diagram, right? And here you can write it as V1 plus V4 is equal to V2 plus V3 plus V5. These are the drops, and these are the rises. Voltage rises, some of the voltage rises equal to some of the voltage drops. This is the Kirchhoff's voltage law. Now take this another example also. This is also if you apply it. So this is voltage rise, and this becomes, though it is a voltage source, but the current we have assumed it as plus 2 minus current is flowing in this VB, and therefore it comes under the voltage drop. Then you can have an equation like this: VA minus V1 minus VB minus V2 minus V3 is equal to 0. Or in other words, we say VA minus VB is equal to V1 plus V2 plus V3. So these are the algebraic sum of the voltage rises, and these are the algebraic sum of the voltage drops. Now for this V1, V2 and V3, now we apply the Ohm's law. What is V1? V1 is nothing but the voltage across the R1. And if I know the current in the R1, if I know the current in the R1 as I, then I can write it as I into R1. Similarly, V2 I can write it as I into R2, where I is same in V2 also, and V3 I can write it as I into R3. So then you substitute them here and then simplify it, you will get the VA minus VP, voltage rises, is equal to I into R1 plus R2 plus R3, and from this one we can also find current I, right? And the current expression is given here. Let us look at this another example, right? Obtain Vx in the figure shown in below using KVL, right? So apply Kirchhoff's voltage law to this loop in clockwise direction. If you apply Kirchhoff's voltage law in for this loop in clockwise direction, then you will obtain it as the equation as like this. Since you have taken is the clockwise direction of current Ix, so this becomes plus 5 volts, right? This becomes plus 5 volts, right? And plus 7 volts, and then minus Vx is equal to 0, or Vx is equal to 12 volts. This is what we got here also. Right. So, and from that one we can find out the Ix is equal to Vx by 100. What is the current in this one? The current, if you apply here in this equation, Vx is equal to, if you apply Ohm's law, Vx is equal to Ix into 100. And from that one, what is Ix? Ix is equal to Vx by 100. And if you substitute Vx is equal to 12 volts, we will get it as 120 milliamperes of current. Then that is about the voltage, Kirchhoff's voltage law and Kirchhoff's current law says that at a junction point in a circuit, the algebraic sum of the currents flowing towards the junction is equal to algebraic sum of the currents to away from the junction. Now, in this example, if you consider that I1, I2 are entering, and whereas I3 and I4 are leaving, therefore we write it I1 plus I2 minus I3, I4. That is, leaving currents I have assumed it as negative, and entering currents I have assumed it as positive. Therefore, the algebraic sum of the currents entering at a junction is equal to 0, or algebraic sum of the currents entering at a junction is equal to algebraic sum of the currents leaving the junction also. And that if you represent it as I1 plus I2 is equal to I3 plus I4, these two are entering currents and these two are leaving currents, right? So this is about the Kirchhoff's current law. Now let us look at an example. Yeah, the count the number of branches and nodes in the circuit of the figure shown here. If Ix is equal to 3 amperes and 18 volts source is delivers 8 amperes of current, what is the value of RA? Right. The hint here it is, you just try it once, otherwise you look at this video, continuously watch this video, then you will get the answer for this one. The hint here for this problem to solve here it is, you need Ohm's law as well as KCL you have to apply here, right? So how many nodes we have here? How many nodes we have here is 5. How many branches? First question they ask is how many number of branches they have asked. How many branches we have? This is one branch 1 and 2, 3, 4 and 5 branches here. The answer is 5 branches. How many nodes we have? Nodes is nothing but the junctions we have. Right. How many nodes we have? Right. And these two put together are one node. These three put together are one node. Since there is no element between this node and this node and this node, therefore this entire thing we call it as one node. Node 1, right? And this is another node, node 2. Then here, all these 4, okay, node 3. Therefore, we have 3 nodes, this one. Then what is if Ix is 3 amperes and the 18 volt source is delivers 8 amperes. 18 volt source is if it is delivering 8 amperes, if the current is 8 amperes. Here, if Ix is 3 amperes, what is Ix here? It is if it is 3 amperes. Then what is asking here? It is what is the value of RA, right? So how do you find out the RA? So this RA can be determined by simply here. This is 3 amperes of current and this is 13 amperes of current at this node. At this node, if you apply KCL, as I mentioned earlier, KCL, if you know, right? So the current, if you assume it as, let the current here, you assume it as some current I, right? In some current I. Therefore, if you apply the KCL at this node, KCL at this node, then what we will get here it is this I is leaving and 13 is entering and Ix is entering. Therefore, I can write it as leaving current. Sum of the leaving currents is equal to entering current. Ix is already given. How much it is 3 ampere. Therefore, I is equal to 13 minus 3, which would be 10 amperes of current in this branch. And if 10 amperes of current is entering at this node, look at here, and 8 amperes is coming from here. And if I assume the current in this one is this IRA, then it would be IRA would be equal to, it is leaving and both are entering. Therefore, 10 plus 8, which is equal to 18 amperes of current. So when you know the 18 amperes of current, then you can find out the applying the Ohm's law, RA, IRA equal to VRA by RA. What is VRA? VRA, you look at here, this diagram, the voltage across this is same as this. That is 18 volts divided by RA is unknown, which is equal to 18. And you will get RA as. So likewise, you can find out by the students, right? See here, RA, you got it as 1 ohm here. Now, this is about the KVL and KCL equation. Now, in the next video, we'll see some more examples.